Hello, our project is accelerating hashing algorithm in Bitcoin mining simulation. My name is Nicole. I'm working with Vicky, Annie, and Francis on this project. With the rise of cryptocurrencies, efficient hardware implementation of crypto hashing functions become more essential, especially for Bitcoin mining, which significantly relies on secure hashing algorithms. Because hashing algorithms require significant computational resources, we want to accelerate hashing performance and mining efficiency using HLS techniques. In our project, we implement and optimize SHA-256 hashing in a simulated Bitcoin mining environment. And hopefully, this project can potentially advance efficiency for compute-intensive crypto applications.
SHA-256, or the Secure Hash Algorithm 256 bytes, is a cryptographic hash function that generates a fixed-size output of 256 bits, or 32 bytes, from an input of any size. Given the input data, the algorithm preprocesses the data by padding the message to multiple 512 bits and parses the message into 512-bit blocks so that each block has 16 32-bit words. Then the algorithm initializes the 8 32-bit initial hash values and integrates message scheduling to these values. This scheduling and transformation happens in the main loop of the algorithm as it expands the 16 message words into 64 words and implements the transformations. These scheduling are mathematical bitwise XOR functions that rotate or shift the bits circularly. The core of the transformation occurs in the main compression loop, where the message schedule and the initial hash values interact through 64 rounds of hashing. There are 8 chaining variables, A, B, C, D, E, F, G, and H, that holds the initial hash values and are updated through the rounds. And each round involves 3 specific functions, the choice function, majority function, and the sigma function. These function includes logical operations of bitwise AND, exclusive OR, and negation. The choice function allows the X input to choose if the output is from Y or Z. Essentially, for each bit index, the result bit is according to the bit from Y or respectively from Z. And then at this index, depending on if the bit from X at this index is 1 or respectively 0. The majority function works such that for each bit index, the result bit is according to the majority of the 3 input bits for X, Y, and Z at this index. Lastly, the sigma function that rotates and shifts the X bit in this case. After each round, the variables A through H are updated and the entire process is repeated for all 64 rounds. After all 64 rounds, the final values of the changing variables A through H are added to the initial hash values. The final 256-bit hash is the concatenation of these updated values.
Following creating the hashing algorithm, a mining simulation was built to use the result of the hashes and compare it with the provided difficulty level to determine whether the hash is valid such that a Bitcoin is mined. In a typical mining situation, this is a point where miners continuously hash until a miner has found a valid nonce and hash pair. In order to add this block to the blockchain for all to see, following the transactions and the block is verified, the nonce and hash pair is used as a proof of work by other miners to determine if the given hash is valid. This process typically takes a long time and requires large amounts of computational resources. So to have the process complete in a timely manner for our project, we have lowered the difficulty level to, instead of looking for hashes with 32 zeros in the front, we hash until we find a result with 4 leading zeros, or our results are capped and we produce a result after a couple of rounds and iterations of the hashing. The diagram shows the idea of the mining simulation and the termination point of the simulation. For our design, data is provided in 32-bit packets as a result of the bit width limitations of the FPGA. So all inputs are streamed into the Z board into 32-bit packets. The input in our case is 20 packets of data. This data includes information to simulate a real point of time while mining, where a block will be used for all the information such as the previous hash, the nuance, and version. The diagram on the right shows how inputted data goes through our mining simulation is hashed twice, and the result is then compared to the difficulty level. Following this, if the pair is not valid, the data is hashed once again and to find a new valid pair. The setup of our system in terms of hardware involves streaming our data through an input FIFO queue to the Z board, and then streaming our data out on the FIFO queue.
Now to talk about optimizations. The first thing that we did was inline and change the floating point types to fixed point types. So our Bitcoin mining algorithm utilizes many logical functions that perform many bitwise operations on the message. Because these functions are small, choosing to inline these functions helped to reduce function calls, overheads, and therefore saved area and better performance. Additionally, we were able to implement everything in fixed point value, which helps reduce resource consumption on the FPGA as opposed to floating point operations.
We can also enhance the performance of hashing through array partitioning. Since hashing requires multiple concurrent accesses to different arrays, without partitioning, all of these accesses are forced to go through a single port memory, which means the access will be sequential. As a result, this will slow down the performance. The sequential access is a bottleneck in hashing, especially for large datasets or in parallels environment. We use array partition as a technique where we split large arrays into smaller independent subarrays that can be accessed simultaneously. This enables parallel access, which means multiple requests can be serviced at the same time. Here is a breakdown of the partitioning strategy for each array and its impact on hashing performance. Based on the type of access each array requires, we apply different partitioning patterns. By doing this, we support two critical optimization techniques, pipelining and loop unrolling, which will be talked in the next slide.
Both unrolling and pipeline pragmas were the main contributors for our optimizations. Many loops did not have many dependencies, so we chose to unroll in cost of resources. This proves to be very beneficial to our performance, reducing about 5 times in latency. And full unrolls were done for smaller and less complex loops, while bigger loops had to be partially unrolled by factoring it out. While used more sparsely, pipelining was applied in some cases where unrolling the loop would cause our resource utilization to spike. By pipelining, we were able to perform multiple operations concurrently to increase throughput and effectively use our resources.
Now we want to move on to talk about the evaluation of our result. Here is the evaluation result for our FPGA implementation on the ECE Linux platform, focusing on the latency improvements achieved by our optimized design compared to the baseline. As you can see in the diagram, for prepare message, both functions were fully inlined in the optimized design, effectively eliminating their latency and improving the overall execution speed. And for compute hash round, the latency reduced from 393 cycles to just 124 cycles. And for hash 1 and hash 11, for hash 1, the function was fully inlined. For hash 11, we achieved a significant latency reduction from a total of 2703 cycles by adding up the baseline hash 1 and hash 11 to 515 cycles, which is a 5.25 speed up by optimizing the execution. And we also were able to get the latency for mine block from around 27K to just around 4K cycles, which is a direct result of our partitioning strategies and improved data access patterns. The overall design can achieve a speed of 6.87 on ECE Linux platform. This demonstrates the effectiveness of our optimizations in reducing computational time and improving system efficiency.
Here is our resource utilization for our Bitcoin mining algorithm. As seen in the chart, by optimizing and getting better performance, there's a trade-off with resource utilization. We were able to achieve a lower latency at the cost of greater use of BRAMs, flip-flops, and LUTs. We believe that this optimization was well worth it because substantial speed up for this algorithm was achieved, as noted as on our execution on the Z board.
Here's a quick demo of our project.
Some potential future work for our project includes increasing the difficulty level. Currently, the difficulty is fixed at a relative simple level, and the simulation is capped so that if a valid nuance is not found within a certain number of iterations, the program can still return a hash value. Some other future work also include combining the hashing algorithm with other algorithms and encoding methods to achieve more functionalities like address creation and mining. We also want to potentially integrate mechanisms to detect and correct errors to improve the reliability of our algorithms in general.